Well, in my first lecture, I explained that I was trying to present a way of axiomatizing quantum field theory, which somehow tried to capture some essence of the spirit of path integrals. And I pointed out that the essence of path integrals, as I saw it, was that it produced something which was completely local on a given space-time manifold. One observed things which were localized at particular points, and everything was somehow meant to be built up from things defined locally. Now, the formalism which I introduced, where, remember, I said a d-dimensional theory gave us, for a closed D-manifold, this means always oriented in Riemannian, it goes to a number. And then we had a way, essentially, of calculating that number if W was split into two different parts along a codimension 1 manifold. So a D minus 1 dimensional manifold, again closed, goes to a vector space, in fact a topological vector space, HM. And a cobordism, of course, went to an operator. Well, so there's an obvious question springs up immediately. Is this vector space somehow made locally out of the space slice M? Obviously, that somehow ought to be true if everything is local in space-time. So is HM, in some sense, constructed locally from M. So an obvious thing then is to say, suppose M were decomposed into two manifolds intersecting along something of codimension D minus 2. So we have a picture like this. Can we assign some kind of objects to H of M1 and H of M2, which we could somehow put together by some strange operation? So these are some kinds of operation which we can somehow put together to give us an actual vector space HM. So why might we want to do that? And how might we go about trying to do it? Well, just in order to somehow capture the essence of what a quantum field theory is, it seems to me that sufficiently motivates that we would somehow try to incorporate something of this kind. On the other hand, there's a more specific reason which I'd like to mention briefly. Remember, I defined, and that's connected with the question of deformations of theories. You see, part of the advantage of this picture is that you're meant to be able to make a moduli space of theories of a particular kind. So you're meant to be able to say exactly, in a precise sense, what it means to deform theories. And I explained already that in the path integral picture, theory is defined by some action functional on some space of fields. And in that picture, to deform the theory is to deform the action functional. And the locality of the action functional says that you change it from a functional s to s plus change in s, where the change in s will be, on some field, will be the integral over the space-time manifold of some particular local thing, let's call it sort of omega x, just very roughly will be something of that kind. And this ought to correspond to something that we can observe in the theory. So, in other words, this thing, omega x, ought to be, in some sense, in the space of things OX, which were the observables. Remember, I defined this vector space of observables, or, if you like, fields, at x, which, remember, I defined as an inverse limit of h of the boundary of a disk when we let the disk run through all disks with x in the interior. So it would be nice to say that any infinitesimal deformation of a theory corresponded to something like this.
Is omega supposed to be a function of phi and its derivatives?
It's meant to be a field. So
Omega x of phi. Is that omega of x of phi?
yes, sorry, omega x of phi.
And that's
Yeah. And it's something, it's a function, it's meant to be a function, yeah, it's something which just depends on phi and its derivatives to any order at the point x. Sorry, yes. Sorry. Yeah. And, but I explained how in any theory in my system we could define this vector space at each point of candidates for such things. Now, I claim that when we put in this additional locality, we have a good chance of being able to prove a theorem of this kind. On the other hand, we have rather obviously no hope at all of being able to prove a theorem of that kind if we don't put in additional locality. In the case, the amount of locality that I'm going to introduce now, just going down to codimension 2, would probably only suffice to prove this theorem in the case of two-dimensional field theories, and they're the ones that I personally am most interested in. I'll explain later why they. Well, I'll explain the sort of sketch of the potential proof of a theorem of this kind when I've said what the formalism is meant to be. Why am I especially interested in deformations of two-dimensional theories? I'll just say a word about that. First, let's go back to one-dimensional theory. Remember, I said a one-dimensional theory just consists of a vector space, h of a point, on which we have a one-parameter semigroup acting, corresponding to a cobordism of length t. We have some operator like this, and these things form a semigroup. Well, how do you classify such things up to isomorphism? The only invariant, well, I'll think of the case of it being unitary. It's not all that much more complicated in general. The only invariant is the spectrum of this operator H. Now, the best known case of one-dimensional field theories comes when you consider a particle moving in a manifold M, or perhaps I called it Z in the first lecture, where you define the path integral over all paths from point to point of Z, and this space becomes, remember, I think I explained L2 of Z, and this becomes the heat kernel. Which can be defined by means of if you think of it as an integral operator, its kernel is defined as the integral over all paths or random walks from there to there, weighted with the action given by the usual energy. Now, in this case, of course, the spectrum then is the spectrum of the Laplacian on this compact manifold Z. This is meant to be a compact manifold for this discussion. And it's an interesting question, a famous question of Mark Katz, to what extent that remembers the manifold M, the manifold Z. If you give the spectrum of the Laplacian, you know quite a lot about the manifold. For instance, if you count the growth of the number of eigenvalues less than x, say, it grows polynomially in x, and the rate of growth tells you the dimension. The coefficient of the leading term in the number of eigenvalues less than x gives you the total volume of the manifold. By looking at more and more careful estimates of the growth of the number of eigenvalues, you can find out things like the Euler number, various topological properties, whether the manifold has a boundary, what the volume of the boundary is, and so on. On the other hand, you can't determine the manifold completely. So there's a map from manifolds to one-dimensional theories which captures something but is rather forgetful. Now, one of the general ideas in two-dimensional field theory, one of the central ideas of string theory, is that there's a corresponding map from manifolds to two-dimensional field theories where the space of fields, remember in the path integral picture on a space-time W we have a space of fields which we'll think of as being the C infinity maps from W into Z, just as this one was made out of paths in Z. And on some, and the action is the usual action whose critical points would be the harmonic maps, the usual energy in the mathematician sense of a map from one Riemannian manifold to another. And so if we're thinking of this as a two-dimensional manifold, the interesting vector space, if we just pursue this picture associated to the circle, would be in some sense, which is difficult to make precise, the L2 functions on the space of C infinity maps from the circle into Z. In other words, the free loop space of Z. Well, this would be called the sigma model, the two-dimensional sigma model associated to Z. Well, there are lots of problems making it, but it's certainly on the edge of being constructible. Now, the idea is that the space of two-dimensional theories is meant to resemble the space of manifolds much more than the space of one-dimensional theories does. On the other hand, this is as far as you go, because if you were to try to make a three-dimensional theory, you might say, well, why stop at two? Then undoubtedly these theories completely won't exist for reasons I mentioned in the first lecture, that the variational property of the energy on maps from something three-dimensional into another Riemannian manifold is completely ill-posed and disastrous. So one has some hope of constructing these theories for each manifold, but one can't go any further. Now, of course, the reason you can't get back, in order to get back the manifold in this picture, you see, if you just know the Laplace operator, what you need is to be able to say how the functions on Z act on this Hilbert space. If you could get back the commutative algebra of functions, of course, we would be in business and we could get Z exactly. Now, in a two-dimensional theory, we can't do that either. But you see, the observables that one has in the theory are at least beginning to be a little bit more like a commutative algebra, because, well, the most obvious observable you would have here, you see, would be to take a function f on Z, so some smooth function, and to define as your field the function, we could define a function f sub x of Z, which was f of phi at the point x. And that would be a function on the space of fields. X is a point in W. That would be a function on the space of fields, which just depends on where the field is at this point. Well, supposing we could do that, and we could then put C infinity of M at Z inside the space of fields at each point x by that procedure, then we would have at least an operator acting on this space for each function they wouldn't form a commutative algebra. If they did form a commutative algebra reflecting the commutative algebra structure of this, we would, of course, be completely home. But I've already, again, said that they form something a bit like a commutative algebra, because if we take 2 points x1 and x2 in a small disk, we always have a map like this, I explained, parametrized by the positions of the 2 points. And that's just by thinking of this as a cobordism to the boundary of that disk. And we can think of this as we think of the center of the disk as being there. We can think of the space of this as being an approximation to that. So we can think of this as a kind of completion of the observables at the center of the disk. And so we have a kind of multiplication parametrized by pairs of points, and it will be up to some deformation commutative, because inside the disk we can move the points around and interchange them. So we'll have something approximating a commutative algebra structure on something which, at least in principle, ought to contain the functions. So there's the idea that a two-dimensional theory ought to look, has more right to look something like a manifold than a one-dimensional theory does. And, yeah.
How do you incorporate duality symmetries into that point of view?
I think that would take us a bit far afield, really. I don't want to.
T-duality?
Can we talk about it another time? I mean, I could talk about that, but it would kind of veer us off into outer space, I'm afraid. So you see, how might we get some idea that the space of manifolds was somehow like the space of theories? Well, if we could say what the tangent space to the space of theories was at a particular point, we certainly know what the tangent space to the space of Riemannian manifolds is, the particular Riemannian manifold, because if you change a Riemannian manifold, you just add something to its Riemannian metric, so you give some kind of tensor field on it. And if you could see that the space of infinitesimal deformations, which wouldn't quite be the space of fields, but would be the ones, remember I said that this thing was acted on in good cases by the conformal group of whatever dimension space we're in. So we'd need something which had the right kind of behavior under the conformal group to be something that could naturally be integrated over an arbitrary two-dimensional manifold. Nevertheless, if we could prove something like about the space of deformations, that would be extremely convincing evidence for this kind of picture. Well, I hope I'll have time to say a little bit more of that at the end of this lecture, but actually maybe I'm not going to. I'll try and say in that case a little bit more about it tomorrow. So the general formalism for factorizing in this problem is to say, so this is the situation we want to study. What we shall try to do is assign to each closed D-2 manifold N a linear category Cn. What's a C-linear category? Well, it has some objects, and the space of morphisms from any object to any other object are it'll be a topological C-linear category in general, will be a topological vector space, and composition of morphisms will be continuous and bilinear. And it will have the property that the categories assigned to a manifold and a manifold with the opposite orientation will be opposite categories. So if n bar denotes m, well, I called it n star in the first lecture. I'm not going to talk about unitarity for the present. So n star was n with its orientation reversed. And I want to give a functor then from this to the category of vector spaces. So this is very schematic for the moment. And this ought to be just the opposite category of this. So the category with the same objects where the morphisms are just the morphisms going in the opposite direction, so to speak. Morphisms from A to B become morphisms from B to A in the opposite category. And when we have two objects, psi in here and eta in here, then you see the homomorphisms, the morphisms in C from psi to eta is a functor from the C opposite tensor C to vector spaces, and that's a vector space, and that ought to be and the natural duality which occurs here. So what we'd like to say is that we assign to a cobordism from an n0 to an n1, so these are d minus 2-dimensional things, a functor, an additive, well, a C-linear functor from Cn0 to Cn1. In particular, this problem should be solved formally in the following way. Well, with the obvious properties obeying. Remember, in the original definition, there were two basic axioms: that when you took disjoint unions of things, everything tensored, and when you concatenated cobordisms, the I'll write this again, UN. The operators concatenated, so I'll just write these two things rather schematically: tensoring and concatenation. So I'm leaving open all sorts of questions is exactly what I mean by the tensor product of linear categories, exactly what kinds of topology, what conditions, all sorts of things. All the problems which you had for topological vector spaces, you have here, only much more so. But at least schematically, the answer to this problem, the formal answer to this situation, is
half of A tensor B to C tensor D is the tensor product of the half spaces?
Sorry, say again?
Just to get a rough idea.
If you want to get a rough idea, imagine, I'm going to give some examples, but imagine the category, you have the category of A modules for some algebra A, and the category of B modules for some algebra B. Then the tensor product is the category of A tensor B modules. So that's the way to think of it. Or, imagine you have representations of one group, representations of another group, then the tensor product is representations of the product of the two groups. Well, you see, so we think of this picture as a cobordism from the empty set to n, and m1. Now, the tensoring property will tell you, so tensoring implies that the category associated to the empty manifold is just the category of vector spaces. So this will be an additive functor from vector spaces to C of n. So it's completely determined by what it does to this, and that will go to some object, which we, I might as well call x sub m1, a certain object of that category. On the other hand, n2 should give us a functor this way, and this should go to the space associated to the union of the two things. Or if you like, if you want to think of this functor as being in the dual category, if you can think of this thing as got by putting together an object x and xm2, so to speak, where these are respectively in Cn and Cn star. And we can put them together to get a vector space. And so if we think of it that way, if we reverse the orientation and think of these as both like that, then this will just be the morphisms in the category Cn from an object xm1 to xm2. Right. Well, so let me first of all very quickly, formally sketch.
Where does that live?
Well, you see, you can think of these. If I were to think of these cobordisms as both incoming, they both give us objects of this category, and then this vector space would be the morphisms from the one object to the other object. So I suppose I should write that as that's meant to be the functors in C, the morphisms in C from xm2, I suppose the way I was writing it, to xm1. xm1, m2 bar, sorry. Star. Okay. So star was reversing orientation of the manifold. I think that's right now. Now, let me very, very quickly tell you schematically why one expects this to enable one to prove a deformation theorem. And then let me give some very obvious examples. And then I want to get to a more analytic example, the case of free bosons. So this is something, this is again going to be very, very schematic. You see, ideally, one would like to be able to calculate the number which a theory, suppose we have a two-dimensional theory, and suppose we somehow extended it to a three-tier theory by putting in this kind of data. Oh, sorry, I forgot one additional thing. We want to associate to each closed manifold this and to a cobordism a functor. So let me, I left out one of the crucial things. Sorry. Supposing we had two different cobordisms. Then think of them very schematically as being like this: n0, n1, a cobordism m, a cobordism m prime. Then it makes good sense to say that these two cobordisms are themselves cobordant. In other words, that there's a d-dimensional manifold, W, which is a cobordism between this one and this one. Now notice that in order to do that, we have to enlarge our picture to have manifolds with corners in them, because this is clearly that thing is a manifold which has not only boundary but has a corner where the two cobordisms separate out. Well, when we have a cobordism W between two cobordisms, remember here we have a functor um and another functor um prime between these categories. So we have two of these things. So we would expect W to correspond to a transformation of functors from um to um prime. So this is the transformation of functors. And it ought again to have the same properties of tensoring and concatenation. But in other words, that means that for any object here, you see we can apply um to it, we can apply um prime to it, and TW is something which does that naturally in X. It's a natural transformation, natural in the variable X. In particular, you see, suppose these two things, let's specialize to the case where M was itself closed, so it was a cobordism from nothing to nothing, then what could this functor be then? It's just a functor from vector spaces to vector spaces, and that will take, just determined by what it does to the complex numbers. It clearly takes it to the vector space for H, for M. And a transformation of functors will just be a map from there to there. So we'll get back the data that we had before, that in the case where W is an ordinary cobordism, we just get back the map between vector spaces that we had in the original setup. Well, and of course, if we could have these two things, M and M prime, also empty, in which case these would just be the complex numbers, and then we would have a TW like that, which would just be a number, and that would be the number associated to the closed D manifold W. So the whole theory is very sort of tightly bound together. But I'm going to give you some examples where you can actually do that, at least in the situation of topological field theories. But let me first of all explain that one of the things we'd like to be able to do if we had this setup is when we have a surface W, a closed surface W, we'd like to be able to use this data to say that we can calculate the partition function, the number which the theory associates to this thing, from quite small pieces. So we might divide this up polyhedrally, triangulate it, but, well, we don't need the pieces to be triangles. So supposing we divide up our W into small curvilinear polygons, like that. Then I'd like to be able to say that you can calculate the number from things you associate just to the little bits of this decomposition. And then we're going to say that we can take a limit over finer and finer subdivisions, and then we will be able to prove a theorem about the deformations coming from local fields. So how will we do this? Well, so just imagine you have this I'll refer to it as a triangulation drawn on the surface. Let's do the following. Let's add a little circle around each vertex. And let's also put in a little tubular neighborhood, very thin, of each edge, like that. And so on. So now we've got an even finer decomposition into curvilinear polygons. And now let's focus on the, so to speak, new vertices we've introduced. Forget about the old vertices. Let's rub them out. And let's focus on the new ones. So where are the new ones? Well, if you think for a second, the new vertices are indexed by flags in the decomposition. You see, this one is named by the fact that it's near this vertex, that edge, and in that face. So whenever you have a vertex contained in an edge contained in a face, you get one of these points. Furthermore, these vertices, new vertices I've introduced, come in two kinds, positive or negative, because the flag can go clockwise or anti-clockwise. You see, this is a positive one because you go that way. This is a negative one because you go that way. So we can divide that set of vertices into two subsets, P and N, equal in number, the positive ones and the negative ones. Now, you notice that there are, in this picture, three cobordisms. So these are naught-dimensional manifolds. So we have three cobordisms in this picture from P to N, which are called V, E, and F, where these are meant to be the vertices, edges, and faces of the original decomposition. So, for instance, F is the cobordism which takes a flag and changes the face that it's in while keeping the vertex and the edge fixed. So you see, suppose we start there. That's something in P. We want to change the face and keep the edge and vertex fixed. So that will be that cobordism that goes from that one to that one. On the other hand, you see, each point is labeled by a flag: vertex, edge, face. And I want to, each of these things will change one of those things while keeping the other two fixed. So, for instance, if we were to apply E to this, we want to change the edge while keeping the vertex and the face fixed. So that will take it to there. I'm sorry, we should blow up the picture of it, shouldn't we? We have one there, you see, one there. This will be one that changes the face while keeping the edge and vertex fixed. This one will change the edge. And we can also change the vertex while keeping the other two fixed. That will be this sort. Okay. Now, I want to now look at the following schematic picture. I'll read time upwards, so to speak. So we start with the empty manifold, and we have two different we first do one cobordism to the union of these things. I can think of the one I'd like to focus on is the one which changes faces. So let's start with this bottom one. So that's no. The one which changes edge, for what it's worth. I want to think of E as a cobordism from the empty set to P union N. Right. So I think of it as a sort of U-shaped cobordism. Each one of these bits. This one I want to focus on for a moment. That seems to be called E, if I've got that right. So think of E as being a cobordism like that. And now think of F as being a cobordism going the other way, from that to that. So we're kind of... See, imagine we had just 3 positives and 3 negatives. We have one thing going like that, and then the other thing I'll write with double arrows going outwards like that. So we have 2 cobordisms which I'm thinking is going from nothing to the set of 6 points. If I compose these 2 cobordisms, clearly what I'm going to get is the union of these circles. So the composite from there to there is just a closed one manifold, and it's the union of these circles. This one was the one which was V, was it? Was F, sorry.
I mean, the circle composed into something which is going around, right? Do you have those circles oriented? Those arrows oriented, right?
Yeah. Well, the flags, the set of vertices come positive and negative according as they curve that way or that way, so to speak. When you go from the vertex, you go from vertex to edge to face. It's either on the left of it or on the right of it. And so we have, maybe you would have preferred me to write this as P union N. So is that what you're saying?
Just talking about your picture with the hexagon.
So the P, we have P1, P2, P3. This is the case where there are 3 edges coming out. And then N1, N2, N3. We have sort of something going that way and that way. Oh, sorry. Okay, no. And sorry. Sorry, please. I don't want to spend too long over this, actually. You can fairly obviously think of the hexagon as a cobordism between 2 sets of 3 intervals, going from a set of 3 points to a set of 3 other points. So we have a cobordism between that composite and the empty cobordism, which fills in all these. Let's call this cobordism V hat. That's filling in all the vertex disks. Goes from the nothing cobordism to all those disks. Well, let's now do this a little bit more curvily, because now let's put in V. So instead of using the ones that go, instead of using these ones, let's use these ones. I've done this wrong, so I'm so terribly sorry. I wanted to think of that as E and that as F. I'm terribly sorry. I mean, it's what I said is still exactly true, I hope. Here we change the face and the edge, so we never change the vertex. So this one goes round the vertex. Here we change the vertex and the edge, we never change the face. So the composite of these two will be the thing that goes round just inside each face, like that. So by filling in all the faces, we get a cobordism to nothing, which I'll call F hat. On the other hand, we've now covered everything except the little strips along the edges, and we have a cobordism from this thing, which fills in the edges. You see, at each point, we have here's an edge of the original picture. We have a cobordism that goes like that, and that was called F. And we have a cobordism that goes like this, which was called V. And so this is a cobordism between two cobordisms. So we can write this as E hat. Okay. Well, so you now see the following thing. That if we know what vector space is associated to each of these little circles, and we know the vector in it, which is the sort of vacuum vector corresponding to filling it in with a little disk, then we know the picture. I'll write this very schematically like that. This is a picture of empty manifold, empty manifold, empty cobordism, and here is P union N. Right, so just knowing the vector space associated to that tells us all of that part of the picture. Now, if we know how to handle this picture, just a very thin rectangle, short rectangle, that will tell us about this cobordism. Finally, we have to fill in all of these things. And remember, this is meant to be a very fine triangulation. And the axioms of the theory will tell us we get the partition function as the composite of those maps. So I never need to know anything which isn't just something happening in this little tiny curvilinear triangle. We do say the typical thing is something like that, or filling in a little disk, or filling in the interior of it. So in other words, at the last step, the cobordism going from here to here, that will correspond to the space associated to all of those circles. So at the last step, we will have the tensor product over all the faces of the space associated to the boundary of each face, and we will put together those things and get into the space associated to the empty set, which is the complex numbers. So suppose we have a one-parameter family of theories now. We're going to deform this. Well, each of these maps will be infinitesimally deformed, and you can see that the total change will have to be the sum of a contribution from each of these little pieces. And we know all about these little pieces because at each little piece what we're actually looking at is something like a vector in a space associated to this or this or this or something, and they are all very good approximations to the space of fields in the middle of the little region where we are, because that's how we define the fields at a point. Well, to do that, particularly when you have a topology, obviously is going to take some discussion. Gosh. I want to keep moving a bit. So, I wanted to mention two examples, and I wanted to do them fairly carefully, but I somehow managed to take too long over that picture. So let me give you just the very, very simplest kinds of examples of where we get interesting examples of purely topological three-tier theories. The simplest invariant you can possibly associate to a manifold is its Euler number. So supposing for a surface we consider its Euler number. Now that's not multiplicative. So if we want to have something that could be the partition function of a field theory, we could pick once and for all a complex number lambda and take lambda to this, or better still, half of it, because I'm talking about oriented surfaces, and the Euler number of an oriented surface is always even. So we have a theory whose partition function is that. Well, now, of course, when you string, this behaves very nicely with respect to splitting things into two, because the Euler number of any one-dimensional closed manifold is 0, it simply behaves additively when you cut things into two. So you seem to be able to build, you can build, a two-dimensional topological field theory where the vector space associated to any one-dimensional manifold is simply the standard complex numbers, and given any cobordism, you just multiply by e to half the Euler number of the cobordism at lambda. So this is a theory which depends on a parameter lambda. Well, so that looks fine until you ask yourself, can you add to it a layer one down? And you see at once that there's a problem. Because supposing you take a two-sphere and you divide it into three parts by two meridians going from the north to the south pole. So perhaps I should look at it from the top. There's the North Pole, and we'll divide the sphere into three regions like that, three lunes, bounded by meridians of longitude. So we divide this thing into three. Well, the Euler number, of course, of the sphere is 2. And here we have three regions bounded by things which are circles but have corners. And one is in trouble because it's very difficult to write 2 as the sum of three reasonable contributions. They should all be by symmetry the same. And so you see that you have to change your ground if you want to get something that actually makes sense. Now, in this case, you can see very clearly what's got to happen. We've got to change this to a one-dimensional vector space which actually depends on this one-dimensional manifold M and is not going to be independent of M. And then we will be able to associate something in this. We will then be able to extend further down. I think
was a closed one now?
Yeah.
Connected?
Not necessary, no. But keep in mind the connected case. That will do. That will be bad enough for what we want. You see, well, I hope I won't confuse people too much if I decide to get rid of this lambda and just write this additively. here, let's think of our partition function as the number, the Euler number, or half the Euler number. And instead of having a line, let's have a z-torsa. In other words, SM. So this is a set on which the group Z acts transitively and faithfully. So it's just an affine copy of Z. We know what we mean by moving n steps to the left or right in this set, but we don't know where the origin is in it. Well, given such a thing, you can obviously make a line because you take the set SM across the complex numbers and introduce the equivalence relation coming from the action of Z on it, where Z shifts this along and Z and the element n in there multiplies by lambda to the n on that number. So that will be a copy, that's a way of getting from a Z-torsa to a line. Now, what is the Z-torsa and what is the category? Well, you see, it's sort of obvious, really, because we want to say that this thing is going to have a point in it for each way. See, supposing we have any even curvilinear one-dimensional manifold M, then clearly what we're going to do is we're going to consider different ways of filling this in with surfaces. So there are many ways of doing that, different genera. They don't have to be disks. And we will then say that we identify one way with another way plus n if the two things together that we put in form a surface of Euler number n. Well, that way we can carry on and modify this. And in fact, I prefer to do one that I find slightly easier to say of the same kind is the case of in 4 dimensions where we have a 4-dimensional manifold cut into 2, and we consider the signature. The signature also adds, just like the Euler number.
Have you finished defining these two?
Well, I didn't do that very well.
Was M supposed to be a closed or an open one then? I mean, this M in your picture here, are there two M's? Or is M an integral or a circle?
M was I better be. I'm just very upset that. Sorry, I think I'd sooner just leave this. Otherwise, I won't be able to say my punchline at all if I explain that properly. Sorry, I'll just have to abandon that, and maybe people can ask me about it afterwards if they want. In fact, I'll also abandon the other case because I really do want to get to my punchline in the next 5 minutes. So one of the features of this approach to field theory is that I think it's extremely good from the functional analytic point of view, because right at the beginning, when I said we wanted to associate a topological vector space to a d-1 dimensional manifold, I was very ambiguous about whether I meant a Hilbert space or what kind of topological vector space or whatever. The reason why you can be very cavalier about that is because, remember, I explained that what M really meant was a germ of a d-dimensional manifold along a d-1 dimensional manifold. So it really meant a sort of infinitesimal cylinder, or a germ of a cylinder like that. So M actually comes with a lot of parallel slices, a germ full of parallel slices, and each of these parallel slices, of course, if M prime and M double prime are two of them, there will be a propagation operator from one slice to the other. And that will be a trace class operator in the axiom system, so it will be something very strongly contracting. So the upshot is that the vector space associated to a d-1 dimensional manifold is a topological vector space with a very strongly contracting semigroup acting on it. So we can form, so to speak, a small space in a big space in the same way that out of the action of the Laplace operator on L2 functions on a manifold, we can make by a direct, we can make the C infinity functions or the distributions by looking at things which on the one hand become L2 when you hit them by the heat flow, or the things which you get by taking something in L2 and applying a non-zero heat flow to it. We can get very smooth functions or very irregular functions by just moving backwards and forwards in the heat flow. And the class of vector spaces with this kind of flow is one which has a beautiful tensor product and extremely good function analytical properties. Now, I want to explain what happens at codimension 2, because I want to say at least what I can do in the case of two-dimensional massive boson theory, where to a codimension 2 manifold, which I'll write here just as a dot n, which we think of as sitting inside a germ, sitting inside a d-dimensional germ, so it's sort of thickened up by this little tube around it. I want to say what we're going to actually associate to that, so as to make a, first of all, the analog of this and how it enables us to solve the patching together problem in two-dimensional field theory. Now, so I'm now going to talk very quickly about the two-dimensional, in general, the d-dimensional massive free boson. And I'm going to say things which won't be tremendously intelligible, I suppose, to people who haven't met anything like this before. But we want to associate to a d-1 dimensional closed oriented Riemannian manifold some topological vector space, and in inverted commas it's going to be the L2 space on the space of smooth functions on M. So that means C infinity functions. Now we want to make some Hilbert space. It is going to be a Hilbert space in this case, or at least it's going to be a Hilbert space when we have the reflection positivity property that I mentioned earlier. We're going to try and define some L2 space out of this. Now, a massive free boson is described by some field equation, and its Cauchy data along when we have a cobordism in this theory, when we have an M, and we're just in the classical theory that this is based on, a trajectory of the field is determined when you give the value of the field on M and also give its time derivative. It's governed by a second order PDE. So Cauchy data for this thing consists of this. So the symplectic manifold of classical states for this theory is this plus its dual, which we can think of this as being in the dual of this, which we can think of as smooth d-1 forms. Now, one way of explaining of defining this space is to say that it's going to contain a certain element, and it's going to have a certain algebra of operators acting on it, and it's going to be the smallest thing which is compatible with that. Now, the way we want to have vectors in this space associated to any W whose boundary is M. So when we have a space whose boundary is M, we can take a field on this space, so an element of this, and extend it to a solution by solving the Dirichlet problem for the classical field equation on this W, and thereby get a map from boundary values to smooth functions on W. We can then take the normal derivative, which phi dot, which lies in here, and that will give us a map from there to there. Or if you like, will give us a quadratic form, the action of the classical solution with boundary value phi. So we can take a Gaussian function in this space. Let's consider functions of the form, this will be associated to a chosen manifold W, by saying that for each such thing we have a Gaussian function which associates to phi the classical action of the solution of the problem with boundary value that. Then this Hilbert space is characterized by the fact that it contains such a vector, and it can be acted on by, on the one hand, translation operators coming from these things. So we're allowed to translate the functions along this vector space, and we're allowed, these things are linear forms on here, we're allowed to multiply these things by such linear forms. So the thing is characterized by that construction. But that means it's characterized by saying it has a certain action on it made out of this thing. It has two kinds of operators, multiplication, action of things here, action of things here, which have certain famous classical commutation relations. They form a certain Weyl algebra. So the important thing is that this is characterized as a representation of a certain Weyl algebra, an algebra made from omega naught m and let's just call that algebra AM.
So far it depends on the choice of W.
Yes, and you prove that it doesn't depend on the choice of W. Yeah, that's right. Well, so I want to explain then how to do the patching in this case. You can define this space even for a manifold with boundary, because you can consider functions which vanish on the boundary, if any, and you can solve the Dirichlet problem when you have an M, which maybe has some boundary. You can consider W's which themselves have boundary, which meet M at the boundary of that, and you can solve again the Dirichlet problem with Dirichlet boundary conditions on that part of the boundary of W.
Sorry, what was the boundary condition?
Just Dirichlet conditions on...
What about the wiggling lines?
Sorry?
What are the boundary conditions on the wiggling lines?
0. Right, so
Zero.
given a phi here which vanished on the boundary, we find the classical solution which vanishes here. Right, so this is defined, it makes good sense for manifolds with boundary. Now, what I want to say is that the solution of the patching together problem is the following, that you associate to the n d minus 2, which it sits inside a little disk full of d minus one dimensional slices which are potential m's, and they can be filled in by between two such things we can fill in d minus two dimensional slices. So what is going to happen is that we're going to, given n, we're going to make a space h m, well, let's call it n plus, for each half line, for each ray coming out into this little disk and ending, having boundary at the outside of that disk. And we're going to say that we have a family of algebras parametrized by these things, and we're going to have a well, I better say it a little bit more schematically first of all, because it will look just too complicated if I try to say it like that. So this is very schematically, and maybe that's all I really have time to say. We're going to associate to n, d minus 2, an algebra a n. We're then going to associate to a n its category of modules. Then, so that's the category, I'll call that Cn. Then we're going to say that to a cobordism like this, n0 to n1, we're going to associate a bimodule. So some vector space on which both of these algebras act. And then we're going to associate to a cobordism between two such things a map of bimodules. So W goes to a homomorphism of bimodules. So I think, I'm afraid, really all I have time to say is to explain in some way what's going to happen. We have our, remember we have our, I'll write it 2 dimensions down. So we have our manifold W, which we're interested in cutting into 2 pieces, W1, no, I'll have to do it on N. M1 and M2. And this is N. Now, if we're just looking, so here we're interested in, well, I've only got one M which is going right through N, so I'm not going to be interested in things which come in at other angles just for the moment. So what I'm going to say is I'm going to take a little neighborhood of this, and I'm going to make the vector space which the theory associated to a manifold with boundary associated, well, we have an algebra associated to this region n plus and to this region n minus. So I have algebras A n plus, algebras A n minus. Then I'm going to consider the space H associated to M1 union n minus, and the space associated to H M2 union n plus. So these are things which go a little bit past there. And then I'm going to take a kind of tensor product, which I'll write as the tensor product over AN. AN is going to be something, some algebra-like thing which contains both of these. Well, I'll write it with an E, And I'll explain what E is in a second. And this is, we're going to have a formula like this, that this is HM. Now, roughly, it's going to be like that this is an algebra associated to N, and this is a right module for it, this is a left module for it, and we are going to simply take a tensor product and get a vector space. But it's a little bit more subtle than that. So all I have time to explain, I mean, don't really have time to explain that, but I'll explain very quickly, is a completely algebraic operation, which is the algebraic version of what's called the Kohn tensor product. So here we have algebra. Suppose we have two algebras, A left, A right, are algebras. And we have H left, H right modules. So this is a module for this, this is a module for this. Suppose we have an additional piece of data, given H, an AL, a tensor AR module, such that each of these is the commutant of the other acting on here, such that AL is the endomorphisms of AR modules of H. And similarly, when you interchange L and R. Then you can define an operation which I'll write like this, which is got in the following way. So you think of, so H is going to be the Hilbert space associated to this little bit. And then we're going to have Hilbert space associated to that, Hilbert space associated to that, and we're going to somehow glue them along there. This is, you take the homomorphisms of AL of H into ML. We tensor with H, we tensor with Hom AR H ML, and we tensor this over AR and this over AL. You see, the homomorph, this has two actions, AL, which we've used up, and AR. So this becomes a right module for AR. Similarly, this becomes a left module for AL. This is a bimodule, so we can form that tensor product. And this is the definition of the Kohn tensor product. So that is that can in the analytic situation can be completed to make a Hilbert space and all that sort of thing. And that's the form of the answer by which you can glue together the state spaces associated to two half manifolds. You have to let them overlap a little bit, then you get an algebra associated to this little piece, and you get this sort of weird tensor product operation which glues the two things together. Now, just to finish very, very quickly, clearly what we really had, corresponding to the vector spaces with one parameter contraction semigroups, which we had for codimension 1 data, here we really had something where we had an algebra for each little radial slice going out of N, and we have a bimodule giving a correspondence between modules for those algebras as we go around. So this thing, this is what's called in the operator algebra theory the Tomita-Takasaki flow. This is something to do with the two-dimensional conformal group of the normal bundle to n in a d-dimensional manifold. And it's the fact that you have this flow which either rotates or goes in and out, which does anything you like in that conformally in that little disk. That's the thing which controls these very large algebras which arise in at least free field theory, which enables you to solve this three-tier problem. I would like to, well, it would take a lot more. I should stop now, so I will just stop, I think. Sorry.